July 2025. Astronomers are stunned when interstellar visitor 3I/Atlas starts emitting an energy signature, not just heat or sunlight, but rhythmic bursts of radiation that mirror the outputs of nuclear reactors back on Earth. A comet is supposed to be a lifeless ball of ice and rock, not a machine with a regulated power cycle. Yet, across observatories the data is the same. Atlas is producing controlled reactor-like energy as it races toward Mars. Who, if anyone, built this? And why is a possible nuclear-powered system now heading for the red planet? The discovery rewrites everything we thought we knew about comets and leaves us facing a question no one expected to ask. Comets are among the oldest objects in the solar system, drifting through space as frozen archives of its earliest days. Their behavior is shaped almost entirely by the sun. As a comet approaches the inner solar system, sunlight strikes its surface, causing the outer layers of ice to warm and sublimate, turning directly from solid to gas. This process releases dust and vapor, forming the familiar coma and tail that stretch for millions of kilometers. The energy output from this activity is modest. Most comets emit less than 100 watts of thermal radiation, about the power of a household light bulb, spread thinly over their entire nucleus. The heat signature is faint, always tied to how much sunlight the comet absorbs at any given distance from the sun. The pattern of energy from a typical comet is unpredictable. Outbursts can happen when surface ice cracks or pockets of gas erupt, but these events are brief and chaotic. There is no internal engine, no cycle or regulation. Instead, the comet's brightness and outgassing rise and fall in response to solar heating, sometimes spiking as new vents open, then fading as material is spent. Thermal emissions in the infrared are weak, fluctuating with the comet's rotation and orientation, but never showing a stable rhythm. Comet modelers at NASA describe these bodies as passive. Their only source of power comes from the sun, and their activity is governed by random fractures and the slow warming of ancient ice. No known comet sustains a repeating or controlled energy output. Even the most active comets, like 29P Schwarzmann-Wachmann or Hale-Bopp, display irregular bursts and fading, never the steady pulse of a machine. The natural expectation, built from decades of observation, is that comets are cold, chaotic, and fundamentally unregulated. There is no precedent for a comet producing energy on its own, or emitting anything beyond the weak, scattered signals of sunlight and boiling ice. July 2025 brings a discovery that leaves even seasoned astronomers searching for words. For the first time, 4 major observatories, the James Webb Space Telescope, the Atacama Large Millimeter Array, Chandra, and the Very Large Array, report a synchronized sequence of energy spikes from 3I/Atlas. The pattern is unmistakable. Every 3 hours, a surge of heat radiates from the nucleus, peaking and dropping off with a regularity more suited to engineered machinery than any known natural process. Spectroscopy reveals the numbers are not just unusual, they're staggering. Peak power output is estimated at nearly 10 gigawatts. That's the equivalent of 10 full-scale nuclear reactors, focused in a body less than a kilometer across. The heat signature pulses with clockwork precision, never drifting or fading the way comet outbursts do. Gamma-ray detectors, tuned for the faintest cosmic flashes, log bursts that rise above the background every cycle. On several occasions, neutron-like events are flagged, phenomena rarely, if ever, seen in comets. Each detection arrives independently, confirmed by teams on separate continents, using different instruments, all converging on the same conclusion. The energy is not random, not chaotic, but regulated and repeating. Avi Loeb of Harvard, long known for challenging astronomical orthodoxy, sums up the mood in a single sentence. The object's brightness profile cannot be explained by sunlight reflection or standard cometary outgassing. It might be generating its own light, possibly from nuclear energy. The data pour in, each new cycle reinforcing the pattern. The 3-hour periodicity holds steady across weeks of observation. No known comet, asteroid, or natural body has ever produced such a stable, high-powered rhythm. The scientific community scrambles to propose mechanisms, but the numbers remain stubborn. 10 gigawatts, gamma bursts, neutron events, all in lockstep, all from a single icy traveler crossing the solar system. With every new confirmation, the sense of unease grows. If these signals do not belong to the familiar world of comets, what kind of system is at work inside Atlas? The question now dominates every discussion, pushing natural explanations to their limits and setting the stage for a deeper investigation. 3 natural explanations have dominated the early debate. Each sought to fit Atlas's energy profile into known physics, but none withstands close scrutiny. First, radioactive decay. Some comets carry trace amounts of heavy isotopes, remnants from ancient supernovae or the early solar system. Actinides like plutonium-244 or aluminum-26 release heat as they decay, sometimes creating local hotspots. But decay curves are smooth and relentless, tapering over thousands or millions of years. The half-life of these isotopes never matches the relentless 3-hour cycle seen in Atlas. No natural sample, even in the most enriched meteorites, pulses with such regularity. Second, the theory of exotic ice transitions. Deep inside some comets, amorphous water ice can flip to a crystalline state, releasing a burst of latent heat. Clathrates, strange cages of gas trapped in ice, can also collapse, dumping energy into their surroundings. Laboratory experiments confirm these events can trigger outbursts, but the timing is always irregular. Heating fronts move chaotically, venting gas and dust in fits and starts. No experiment has ever produced a thermal pulse that repeats with the mechanical precision logged in the Atlas data. Third, frictional heating from internal slippage. Large, fractured cometary nuclei sometimes undergo sudden shifts, layers grinding past one another as the sun's heat seeps in. This can spark outbursts, even drive jets of vapor, but these episodes are brief and violent. The energy released is gone in minutes, leaving behind a quiescent surface until the next stress builds. The observed power curve from Atlas, with stable peaks and measured drops, finds no analogue in this kind of event. Harvard's Planetary Lab, reviewing the full dataset, notes that none of these mechanisms, decay, ice transitions, or friction, can account for the sustained rhythmic output. The search for a natural cause narrows, and with each failed hypothesis, the need for a new framework grows sharper. Patterns in nature rarely keep perfect time, yet, as the weeks pass, the 3-hour cycle in Atlas's energy output refuses to drift. Each pulse arrives with a precision measured down to the minute, tracked by observatories on 4 continents. The odds of a natural process holding this schedule across a rotating, tumbling nucleus exposed to changing sunlight fall to statistical noise. Analysts run simulations of every known cometary mechanism. None produce the unwavering cadence now logged in the data. Radioactive decay, with its slow, even fade, cannot be forced into a metronome. Ice transitions, even under ideal laboratory conditions, break down into fits and starts. Internal slippage from fractures or tidal stress is chaotic, never clockwork. The data from Atlas, plotted over weeks, forms a sawtooth, power surging, peaking and falling away, then repeating with mechanical regularity. Unfiltered, the numbers line up as if driven by a regulator, not by chance. Statistical tests pile up. Fourier analysis of the infrared light curve returns a single dominant frequency, 0.333 cycles per hour, matching the 3-hour interval. No secondary peaks, no drift. Duty cycle measurements, how long each surge lasts compared to the quiet, remains stable to within 1%, cycle after cycle. The pattern is not just persistent, it is enforced. In the natural world, even the most stable pulsars show more jitter. Comet modelers, faced with this discipline, begin to speak in the language of engineered control. Terms like load balancing, feedback, and regulation enter the conversation. The possibility of a designed system, one built to maintain output regardless of external conditions, no longer sounds outlandish. The evidence does not fit the mold of passive ice and dust. It suggests a system built for consistency, a system that, by all available measures, behaves less like a comet and more like a machine. Inside a nuclear power plant, Energy flows in cycles, steady, repeatable, tightly regulated. Operators monitor load balancing, adjusting control rods to keep output within precise limits. The typical regulation period for a large terrestrial reactor is about 4 hours, with minor fluctuations smoothed by feedback systems. Every cycle, the plant produces a signature pattern, a rise in thermal output, a controlled plateau, then a measured decline. Radiation monitors track bursts of gamma rays and, in some cases, neutrons, all held within expected parameters. This is the language of engineered control, predictable, disciplined, enforced by design. The energy profile from 3I/Atlas matches this cadence. Every 3 hours, its nucleus emits a pulse of heat and radiation, peaking and falling with mechanical precision. The cycle is so regular, so unfazed by the object's rotation or changing distance from the sun, that it mirrors the output of a reactor running at full load. Gamma ray detectors log surges that rise and fall in lockstep with the thermal peaks. Occasional neutron-like signals appear just after the heat spike, echoing the secondary emissions that follow a fission event on Earth. Michio Kaku, speaking in a recent interview, drew the parallel directly. If these emissions repeat with clockwork precision, our science demands an explanation beyond business as usual. For researchers used to the chaos of natural comets, the discipline of these cycles is unmistakable. The numbers line up with the kind of system designed to maintain output, not simply react to chance. In the data, the signature of regulation stands out, an energy rhythm that, so far, only reactors have been known to produce. Atlas's tail defies the textbook image of a comet. Rather than streaming directly away from the sun, high-resolution photometry tracks a persistent bend of nearly 15 degrees toward the solar disk. The angle holds steady across weeks, even as solar wind conditions fluctuate. This isn't a random kink or a temporary plume. Measurements from the James Webb Space Telescope and the Very Large Telescope log the deviation at every pass. The result? A tail that seems to steer, not drift, as if responding to internal commands. Brightness pulses ripple through the coma in perfect synchrony with the 3-hour energy cycle. Every surge of heat is matched by a sharp optical spike, then a rapid fade. Automated telescopes in Chile and Hawaii capture the pattern: flare, plateau, decline, repeat. The rhythm is so precise that some observers begin to refer to it as a heartbeat. The pulses cut through background noise, holding to a schedule that would be impossible for a body governed by sunlight and chance. Companion objects add a final layer of intrigue. 3 small masses, each less than 100 meters across, are detected trailing Atlas at fixed intervals. Their orbits are staggered, yet each one brightens and dims in step with the main object's emission peaks. Ground-based radar and space-based imaging both confirm their presence, ruling out debris or background stars. The companion's movements suggest coordination, not coincidence, like tenders shadowing a ship, drawing power or instructions from a common source. Inside NASA's control rooms, the mood is tense. Teams review the data again and again, looking for flaws or overlooked explanations. But the anomalies persist. A tail that bends against the solar wind, a light curve that ticks like a metronome, and a flotilla of companions in lockstep, all pointing to a system with its own logic, its own plan. Mars mission teams face a scenario they never rehearsed. In October 2025, 3I/Atlas will pass within 0.053 astronomical units of Mars, just under 8 million kilometers. For engineers at JPL and ESA, that number triggers a scramble. The object's projected emissions, if the reactor-like cycle holds, could deliver radiation doses far beyond any seen since the dawn of interplanetary exploration. Some speculative models warn of up to 10,000 rad per hour at peak, a figure that would overwhelm the shielding on current Mars orbiters and surface rovers. Perseverance, MA5EN, ExoMars, all designed for the slow trickle of cosmic rays and the rare solar storm, not for a barrage that rivals nuclear testing. Even a fraction of this dose would fry unshielded electronics, corrupt data, and risk permanent loss of contact. Teams rush to revise contingency plans, debating whether to power down instruments, reorient solar arrays, or attempt last-minute software patches. For now, mission leads can only watch the data, run the numbers, and hope the warnings remain theoretical. The possibility of a real, measurable radiation surge from an interstellar visitor has turned routine operations on Mars into a high-stakes gamble. Oumuamua's unexplained acceleration in 2017 set off the first wave of speculation. 2 years later, Borisov arrived, volatile-rich, but still within the boundaries of comet science. Now, 3I/Atlas enters the record as the third interstellar visitor, and the odds of witnessing such a sequence, 3 in less than a decade, stand at less than 1 in 20,000. Astronomers and policymakers alike are forced to confront a question that once belonged to science fiction. Are these objects arriving by chance or by design? Neil deGrasse Tyson, never one to shy from public debate, puts it bluntly: if it walks like a reactor, quacks like a reactor, well, this would be big, really big. In congressional hearings, lawmakers press NASA for clarity, while international agencies quietly prepare their own briefings. The debate spills beyond academic journals and into the global consciousness. For the first time, the possibility of deliberate interstellar arrival is not dismissed out of hand. Each new detection draws more scrutiny, more voices, and a growing sense that the solar system is no longer a closed stage. The pattern, once dismissed as coincidence, now demands a reckoning. In July 2025, telescopes worldwide recorded 3I/Atlas emitting energy cycles peaking near 10 gigawatts, with 3-hour regularity confirmed by JWST, ALMA, and Chandra. These findings sharply contrast with the weak, chaotic energy signatures of typical comets, and natural mechanisms like radioactive decay or phase changes have failed to explain the rhythmic power surges and matched gamma and neutron emissions. Documented parallels to terrestrial nuclear reactors, combined with synchronized tail movements and the presence of 3 companion objects, have led respected researchers to consider a non-natural origin. Yet, NASA's official statements remain cautious, citing unexplained emissions and holding back full data release. With Atlas set to pass Mars at 0.05 astronomical units, the risk to orbiters and habitats is real, even as debate continues in scientific and political circles. The evidence forces a reckoning. For the first time, an interstellar visitor shows energy control that matches no known natural process. What remains classified is the intent, and whether Atlas is truly the first active craft humanity has ever observed.